So then what does our timeline look like for the end of the semester here?
So the timeline, okay, so we have, obviously we have today, we don't have a class on Thursday because of Thanksgiving. So the timeline looks like this. So let's see. What was today's date? November 24th. So November 24th, that's today. We will do a combined loading example, and I will start beam deflection. And then our next class will be November. Oh, is that November still? Let me look at my calendar. No, it will be December 1st. So this is December 1st. That'll be a Tuesday. We will talk about and December 3rd is our last class. It's a Thursday. We'll have homework number 12 is due, and we will review for the final. And our final will be December 8th. December 8th, it's a Tuesday. It'll be a comprehensive. By nature, it's comprehensive, but obviously it will be tailored towards, we'll talk about those. When we talk about the review, we'll talk about the final. So we have 4 more classes. And then, when did I say your project due?
December 4th, I believe.
December 4th?
I think so. That's what I have on my calendar.
I can give you guys more time. Do you want more time? Would that be beneficial?
Let's see, they said the final is the 8th. Yeah. Wouldn't mind having some more time, I guess.
Okay. We give you to do December 11th, but I have to have it December 11th so I can grade it. The grades have to be in the week after. So that's your project. So I'll modify the project due date from the 4th to the 11th. So that's our schedule for the next couple weeks. That's it. Any questions about the schedule? I am going to teach this class again next semester. And
I'll be looking to retake it in the fall.
Okay, but you're more than welcome to sit through it next semester if you like.
Okay.
Email me and I'll add you to my course shell, and you can just join the class.
I appreciate that. They're possibly looking at making me a live-in patient. We're doing infusions and some other stuff.
Okay.
So,
well, if you need to, if you want to join us, you're more than welcome to. Just let me know in advance so I can.
I really appreciate the offer.
Yeah, sure. I offer that to really anybody who wants to learn the material. It's, it's a great subject, and I like teaching it. And the more the merrier, as far as I'm concerned. Especially people who are interested in learning. That's what makes it more fun for me. Makes it more gratifying for me. The people that really want to learn this material. Not that anybody in this class does not, but there are some people that obviously want to just get the grade and move on. But it's an important subject matter. All right, anyway, I'm not going to babble on about that. Any questions about the schedule? Okay, if not, I'm going to do an example. So this is a bar. It looks like this is a rectangular cross section. And here's what it looks like. This end is fixed. And we're applying forces. So I'm going to define some coordinate system. Let's see, along the length, z-axis. So I'm going to change this around. This is x-axis. This is y-axis. And we're applying these loads. We're applying (24 kip), and then we're applying. That's in a negative z direction, pushing on the, compressing it. And then I have 2 kip in the negative x direction. So you could write these in vector form if you wanted to, but those are it. And then this is right in the middle of the top section. This is right in the middle of it. At some distance, we're applying a force in the negative y direction right there. This distance is 4 inches. This force is 3 kips. 3 kip. Okay, so we have these 3 forces, and this cross section is a 6-inch by 4-inch. So 4x6 cross section. And what else? We want to determine the normal and shearing stresses at H and K. H and K. Well, H and K are over here at some distance, 15 inches from the end. So this distance is 15 inches. And H is up here, right in the middle. H. K is right there. And K is not in the middle, it's 5 inches from the bottom. Right. So that's all I got. We want to find out what the state of the stresses are basically at those 2 elements. Now we're not looking for the principal stresses or the maximum normal stress or maximum shear stress. We just want to know the state of the stress at those two locations. Okay. So what I really need to know is how do these forces transmit, or how do they act? What kind of forces and moments they produce at the cross section, which contains both H and K, 15 inches from the free end. So let's see what that does. So I'm going to cut this beam right where H and K are. So here's what I will have. So draw it a little bit more. It's a 6x4, a little bit more to scale. And there's the fixed end. H is right up here. That's H. And then K. All right, well, there's H and K. Okay, so let's see what happens here. And this is the this is the centroid of the cross section. Right there is the centroid. And as far as the coordinate system, this is X. This is my Y-axis. And then along the length is the Z-axis. So I have compressive force, and that force is 24 kip. And I call this P, right? This is the axial force we call P. So that's P. And let's see what else. This 3 kip causes Vy. That's the direct shear in the Y direction. This 2 kip causes direct shear in the X direction. And I can put these in there, I guess. And P is 24 kip. And what else do I have? This times the distance of 11 inches. It's a distance from here to here is 11 inches from 3 kip to where the cross section contains H and K is 11 inches. That is 15 minus 4. That produces a moment. So the moment is always R cross F, right? R from where I'm taking a moment at, or the cross section is. So the fingers of the right hand in the direction of R. R goes from, again, the cross section that contains H and K, that cross section, to where the force is applied, R, in that direction. Cross F, my thumb is pointing in the X direction. So I have a positive moment in the X direction, which is going to be 11 times 3. So this will be 33, 3 is kip, that's in inches. So this is kip inch. That's the moment in the X, and the direction of rotation that it produces is this. Right-hand rule. Is that okay? And then the same thing for that force. R, again, R is going from here, from where the cross section is, all the way to where the force is applied. Fingers of the right hand. Cross F. My thumb is pointing down, so that's a negative Y. So I have a moment. Which will be, now this distance is 15 inches times 2 kip. So I'm not writing in terms of, obviously the direction is defined by these arrows, right? The direction is defined by the arrow. So if I want to write this in terms of this vector, this mx would have been negative 33 kip inch, no, negative 33 I kip inch. And this moment in the y would have been a negative 30 j. So this is 30 kip inch. So we're just simply writing, this is the magnitude and that's the direction. And that will produce a rotation that is going to be like this. And that's all I have. So I have the P, the axial compressive force, and I have two direct shears, one in the X, one in the Y. I have two bendings. These both cause bending. Neither one causes a torsion. Neither one is a torque. A torque would have been a moment in the Z direction along the length. That would have twisted this. I would have caused this kind of twisting. Either a positive Z or a negative Z into the length of the bar. So I have bending in two directions. All right, so any questions about this? So
I don't have any questions on this.
yes, no, you don't have any questions. Thank you. Matt, you're good with this?
Yep, all good.
All right, so let's look at them individually and see what kind of stresses they produce. So, and then I'm going to look at each one of these sections individually. So I'll start with H. This is for element H, or you can say location H, or whatever you want to call it. P, the axial load P, causes stresses along the length. Length is Z, so this is sigma Z. And since it's compressing it, it's a minus 24 times 10 to the 3 divided by cross-sectional area. Well, it's a 6 by 4. So that's pounds. This is inches squared. So what is 24,000 divided by 24? Well, it'll be 1,000, right? This is a minus 1,000 pounds per square inch. So that's what P does. How about Vx? Vx is a direct shear. As far as Vx is concerned, this causes shear stress. This is shear stress due to bending. And element H is right at the middle where it's the highest Q. So this causes shear stress. The shear stress will be on this face, on the leading face right here, in that direction, the same direction as the internal shear, Vx. So that is Z plane and pointed in the X direction. This is tau Zx. This tau Zx, let's see, will be VQ over IT. But for the rectangular cross section, we derived a simpler equation. That simpler equation, I don't recall off the top of my head. But I think it's 3V over something. He talks about those, and I don't have it in front of me. There it is, 3V over 2A. Okay. So shear stress does not have a sign. But again, we can assign a sign based on direction. So I'm going to assign, if it's pointing in a negative x, I'm just going to put a negative. So when I add or subtract, I will find out which direction is the dominant one, and that's the one I will take the sign off at the end. So and this just simply defines a direction. It's not like normal stress. Normal stress, negative means compression. Here, it just simply means that's the direction. All right, so we're going to deal with that. And minus, again, it was 3vx over 2a. Yeah. So this is minus 3 times 2 kip, 2,000 pounds divided by 2 times the area. So that reduces to 2, that's a 4, 16, 2 divided by 16. 2 divided by 16. No, wait, that's not 2, that's 3 divided by 16. Yeah, 3 divided by 16. 3,000 divided by 16. 187, no, I can't do it.
125?
Okay, that's 2 divided by 6. Yes, 125. Negative 125 pounds per square inch. Negative 125. Okay. Next, we'll look at Vy. Vy also produces shear stress. And that shear stress would be 0 because Q will be 0. It's top section. So this one is 0. Is that okay? This does not produce any shear stress. And this shear stress would have been Zy, tau Zy. We don't have any. Next, I'm going to look at My. Let's just do My for next. So it's bending. It's going to bend this entire beam this way. So this half will be in tension. This half will be in compression. And this is at the centroidal axis, neutral axis, and therefore there's no stress. Next, the only thing left is Mx. Due to Mx, top the top will be in tension, and this is the furthest away, so that will have the maximum. Top will be in tension, so sigma z is going to be a positive. Mx, and this is 3 inches divided by Ix. And Mx is 33 times 10 to the 3, that's in inch pounds, times 3 inch, divided by moment of inertia about the x. Moment of inertia about the x, so that is going to be 4 inch base times height cubed over 12. This is going to be inches to the 4th, so this will be pounds per square inch. What will I get? $1375 psi. Okay. All right, so that's what we got. Any questions about these? So now I need to either add or subtract or do whatever I need to do. So let's see. these are both in the z direction. This one's negative, this one's positive, so the sum is, so sigma z will be 1375 minus 1,000, which is going to be 375 psi. And then as far as shear stresses, that's all I have. Tau zx, which is equal to tau xz, will be equal to, and negative. Negative means it just simply defines a direction. So I'll take care of the negative here in a minute by the direction. So this is element should have drawn this a little bigger. This is element H. As far as a coordinate system, X, well, Z is along this way. That's X and Z. So X is going this way and Z is going along the length this way. So that's element H. Sigma Z is 375. So you must have a coordinate system associated with this element that matches the coordinate system and the orientation of element H. And then so we have sigma Z. There it goes again. And then tau ZX. Tau ZX negative, meaning going that way. That's the negative part of it. It's going in the same direction as the VX was. So this is, now we don't put the negative in here anymore, obviously. Tau ZX, the X direction. That's equal to 125 psi. So if that exists, this one exists, this one, and this one. So that is element H. That's the state of the stress for element H. That's our results for element H. Any questions about that? Is our job done? No. On the exam, I will ask you to take this to the next step, which is taking this to more circle and finding principal stresses and principal planes and maximum shear stress and so forth. Okay, so that's element H. How about K? I don't know why I switched to a red pen, but I will continue. 114. Element K. P causes axial stress in the Z direction along the length, which is the same as we had before. So let's just go down the list. Next we did VX. VX, which one is VX? This is VX. As far as VX is concerned, it's going to cause direct shear due to bending, and K is on the top surface, so that is 0. So that's due to VX. Due to what was next? We did VY next. Okay, VY. VY is this one. As far as K is concerned, it is not on the top surface, so it's not 0, and it's not in the middle where it's the maximum. It is at some distance. What's the distance? That's 6, that's 5, so it's 2 inches from here. This distance from here to here is 2 inches. All right, 3 to the centroid, and then 2 more. Okay. So So as far as Vy is concerned, if this is the cross section, and the centroid is here, and this is my y-axis, and this is my x-axis. Each side is 3 inches. This is the 2 inches. This is element K at 2 inches. And that remainder, obviously, is 1 inch. So I cannot use the equation I did before for element H, what gives me the maximum on the surface, 3v over 2a for rectangular cross section. I cannot use that equation. So here, tau, let's see, this will be tau. So if this is the cross section, this, and this is my, no, I didn't want to draw that, that's wrong. X-axis, this is y-axis, this is Vy, and element K is over here. So the shear stress on this face is in the same direction as Vy. I'm going to call that negative because it's a negative y direction. And this will be tau z face y direction, z face y direction, which is same as tau yz. Okay. And this will be negative Vy q over I y. IY? No, it's Ix. The subscript of the internal, the direct shear and the area moment of inertia have to match for normal stress and bending, but not here. So if I'm applying this, it's Ix. Vy causes moment of inertia. The equation that I use for the moment of inertia that I use in the equation is Ix times the thickness. So so this is Q for location K. So this is the Q for here, this location. So I can either use the area above or the area below. So I'm going to use the area above. This Q will be the area, which is 1/4, times the distance between the centroid of it and the centroid of the entire cross section. So that would be 2.5. Distance from the centroid to the centroid of the entire cross section. 2 inches to get to here, and then 1/2 inch. So Q is 10 inches cubed. So let's put the stuff in here. Minus defines the direction in a negative y direction. Vy was what? 3 kip, 3 times 10 to the 3 pounds. Q was 10, that's inches cubed, divided by Ix, moment of inertia about the I-axis. Okay, so this is okay. The same moment of inertia we had over there, Ix. So this is 4.
72.
What is it?
I think it's 72.
72, okay. Inches to the 4th. Thickness. And thickness is this way. And that is 4 inches. Okay, not this way, right? It's this way. And well, I will get the tau yz. And whatever that is, negative 104.2 psi. That's what I have in my notes. Okay, so we have took care of 3. What's next? We'll go in the same order. My. What does my do for element? Okay, so that is on the surface that contains the maximum distance away. So as far as my concerned, this side will be in tension. I'm just going to bend it this way. Going to bend it that way. This side will be in tension. The left side will be in compression. So K is in the outmost surface. So it will produce a stress along the length. It's going to be in tension, but leave it in positive. My is 30. I'm just going to write the equation. My distance will be in the x direction over Iy. So My is 30 times 10 to the 3 pounds. Distance x is 2 inches. 2 inches. Divided by Iy. Iy, moment of inertia about the y-axis, is 6 times 4 cubed over 12. And this would be inches to the 4th. Oh, moment is inch pounds, right? Kip inch, which is, okay, that's right. So sigma z, and this will be in tension, so we left it positive. Sigma z due to My. 1875 psi. All right, so I have that, I have this, I have this, and I have that.
Can you move the paper up a little bit?
Yes, sorry about that. Next, we have Mx. Mx. Well, Mx causes bending like this. So the top will be in tension. The top of the cross section. Anything above here is in tension. Well, K is above there. But it's not all the way to the top surface, it's some 2 inches to the top. So that will cause Mx will cause normal stress in the z direction along the length. It is Mx, the distance will be y, divided by Ix, and it's in tension, so I leave it positive. Mx is 33 times 10 to the 3 inch pounds. Distance y, well, the distance y is 2 inches. Divided by Ix, which was 4 times 6 cubed over 12. This is inches to the 4th. And this one will be 916.7 psi. So now I think I got everything, right? I took care of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, I have everything. Okay, so now I can add or subtract. So first I'm going to look at the normal stresses in the same direction. They're both in the z direction. Both in the z direction. So sigma z is 1875 minus 1,000, which is 875 psi. So I took care of that. This one is 0. This is tau. That's the only tau I have. Wait a minute. There's another sigma z. I didn't do this right. I can't erase it. plus 916.7. That's 1790. 1875 minus 1,000 plus 916.7. 1791.7 psi. Okay, so I almost forgot that one. There's three of them, right? 1, 2, 3. Okay, so that's sigma z. And then shear stress, that one's 0, and this one is the only one I have. Tau yz, which is same as tau zy, is 104.2 psi. And negative mean it's in the negative y direction. That's all that means, negative y direction. So here's, draw this a little bigger. Element K. Element K, going up is the y-axis. Along this way is the z. Right? This is the z-axis, like this. This is the y-axis. That's what I have. So the shear stress, I already have it in the same direction as Vy, and it's a negative y, so I am going to put that right there. This face is the leading edge of that element K. And its shear stress is tau zy, 104.2, 104.2, is in the same direction as the shear force, the Vy, the direct shear. So based on that, I have all the other ones. The only other thing I have is sigma z, and that is positive. So I have sigma z like this. I'm just going to put 92. So that's my answers. Answer for element K and the element H we had before. Any questions for me about this?
I have no questions on this.
Thank you.
Okay, thank you.
You're welcome. All right, so let's move on to section beams, chapter 9. Okay, so I'm going to refer you to my derivations in my notes. I don't want to derive the equations, but I want to show you what to use. So if I have a beam under some type of loading, it could be a distributed load of some shape. And I'm supporting it at the ends. So I have a support and a support 2. This is called simply support. And this beam made out of material E has a cross-sectional geometry that gives you I. This thing is going to bend, right? This is going to deflect like this. And it's going to be stresses associated with these deflections. We're going to define the deflection. We're going to define the deflection by this y. So y of x is a function of the length is called the elastic deflection curve, or simply deflection in the y direction. Why do we call it elastic? Well, because we're dealing in the elastic region of the curve. We're not having, it's elastic deformation. So when I remove the load, it returns back to its undeformed shape. There is no plastic deformations. The equations that we have derived in my notes or in the book, the equations I'm going to talk about that are not valid for plastic deformation. So why do we even want to know deflection? Well, deflections could be a criteria for failure. Even though I don't have actual cracks or failure of the part, deflection could be severe enough that could cause parts to rub against one another or contact one another, or if it's a rotating object and I'm loading it, and if it deflects, well, it could fall off the bearings, or it could cause noise, it could cause vibration. The deflection is a criteria for failure as well. For example, a building, if I'm walking on a bridge and the bridge is deflecting under my feet, that doesn't feel so good, right? So that could be a cause of concern, even though it might be structurally robust, that it does not separate or break or fail. But the deflection itself could be a cause of some concern. And in
I have a question.
Many cases of failure, yes.
With the elastic deflection, does that take off like the fatigue life cycle of a component?
No, it doesn't have anything to do with any of that.
Okay.
It just simply gives you how much is it going to deflect as a function of the length.
Okay.
It doesn't have anything to do with the fatigue or if it's going to live, or it just simply calculates the amount of deflection.
Okay.
Now, to figure out if it's going to live or under fatigue type of loading or impact loading or whatever loading, then that's a different types of analysis altogether.
Okay.
You will study those later in some kind of a mechanical design course. So, but the fundamentals here will carry on to next classes as well. A couple things. So deflection is what we're gonna find this elastic deflection curve. That's the whole goal of this chapter. Derive an equation for the elastic deflection as a function. Obviously, it's a function of the length x. And also, we want to know the slope. So, for example, at any point, if I draw a tangent, to that point, I can find the slope, which is theta x So if slope of the tangent line, basically it's the rate of change of y over x, rise over run, dy over dx, which is tangent of the angle, tangent of this angle. If I draw a tangent line, that will be the angle with the horizontal. Tangent of that angle gives me the slope. And for small deflections we're dealing with are very small, then the angle itself is very, very small. And the slope of a small angle, or tangent of a small angle, tangent of theta x, will be simply theta x, or small angles. Therefore, I can simply write dy dx as theta x, which is, again, the slope. So the equation that I want to talk about is this. This is equation 9.4 in your book. This is the governing differential equation second order. Differential equation for elastic curve. Okay, so the derivation is in my notes and it's in the book, but I'm just going to write it. It's a second order power 2. It's related, so that's related to the internal moment divided by EI. Elastic modulus, material property, geometric property, area moment of inertia, and the internal moment. So that's the governing second order differential equation for the elastic curve. So how do I get deflection from that? Well, if I integrate this twice, I get deflection. If I integrate it once, I get slope. So let's do an example. Obviously, I have to have some boundary conditions because there will be some integration constants that I have to deal with too, and we'll talk about boundary conditions in a minute. So let's talk about the problem like this. We have a cantilever beam with the end load P. This is X, this is Y. And this has some length L. This point is A, this is B. So this is a beam AB. I want to find the elastic deflection curve and deflection at B and the slope at B. This is what I want to find. So we're going to, first of all, we are going to find the reactions at the support. The reactions at the support, I think you can probably do that now without writing the equations. The reactions at the support. Be a P equal and opposite to that. This produces a moment. There's a reaction moment that this type of support produces. P times L clockwise, there'll be a P times L counterclockwise here. So that's the reaction moment, that's the reaction force. In this equation, this is the internal moment as a function of the length. So I need to find out what that is. To do that, I'm going to section this. So I'm going to section it at some length X. And at this end, I have the P and PL, which is the moment. At the cut section, if you remember, there are three, I could have three items: the internal shear, the internal axial force, which in this case is 0, and an internal moment. Now, why do I draw them in those directions? Well, this depicts on the left side a positive v of x. This depicts on the left side a positive moment. So I've drawn these, I've defined these in the positive internal sign convention. But what I'm interested in is this. I don't care about v of x. I'm not going to even worry about that. So I am going to say some of the moments at x equals 0, at x meaning here, or at the cut. And what will I get? I'll get mx, get p I get P times L. I get two moments, mx and P times L. There they are. And then I'll have a negative px. Any questions about this?
No questions. Let's review.
Yes, moment at x. Px minus PL. And I can factor out P, be x minus L. So this is moment as a function of length, anywhere along the length. I only have one load at the free end. So this describes the moment anywhere along the length from x equal to from 0 to L. That's the equation. Okay, so now I'm going to use my governing second order differential equation, which says d squared y over dx squared is equal to the moment over EI. So this is equation 9.4. Multiply both sides by EI. I'll have EI d squared y dx squared is equal to, I'm going to rewrite this, px minus PL, just write it like that. I guess I should have never factored out P, but that's okay. So now I'm going to integrate with respect to x. So I have EI dy dx is equal to px squared over 2 minus plx plus c1 plus c1. Integrate again. EI y of x is equal to px cubed over 6 minus plx squared over 2 plus c1x plus c2. Got two integration constants. Let's look at boundary conditions. So this beam, I'll draw it again, of length L with the end load P that is fixed. This is going to deflect like this. Just going to draw the exaggerated deflection. It's going to deflect like that, right? So this location is at x equal to 0. This location is at x equal to L, right? So we got. Notice that it does not deflect at L, right? At x equal to 0. Sorry, at x equal to 0. So I can write the boundary conditions that the deflection at x equal to 0 is 0. Also notice, since it's fixed, the slope at that point at x equal to 0 is 0. So I can write that dy at x equal to 0, dx is equal to 0, which this is simply slope at x equal to 0. So those are my two boundary conditions, and I need two of them because I have two integration constants. So first of all, I'm going to apply the first one. Y at x equal to 0 is equal to 0. So this is 0 is equal to 0, 0, 0, C2. Right? And I put in x equal to 0. These three terms are 0, and that's also y at 0 is 0. So that's what I get, C2 is equal to 0. So now I have this equation that is EY, y of x is equal to px cubed over 6 minus plx squared over 2 plus c1x. I apply the second boundary condition. The second boundary condition, I can apply it to this, really, right there. or I can take a derivative of this with respect to x. It'll be the same equation. So EI dy x dx is equal to px squared over 2 minus plx plus c1. Same as that. Same as that. Take a derivative of this or take that equation. It's the same thing. So I'm going to apply second boundary condition. dy at x equal to 0, dx is equal to 0. So 0 is equal to 0, 0, c1. Well, c1 is also 0. So both c1 and c2 is 0. So my equation for elastic curve or elastic deflection curve is the following. Write it in terms of y of x. Y of x is equal to, there it is, 1 over EI times the quantity px cubed over 6 minus plx squared over 2. And I can factor out more stuff if I wanted to. I guess I can factor out a 2 and a p, or 6 and a p. Can I do that? 6 and a p, yeah. I can do p over 6 EI times p over 6 EI. So this becomes x cubed. This becomes 3 lx squared. 3 lx squared. So this is the equation for elastic curve right there. All right, so that was part of it. So we wanted the equation for elastic curve, and we need a deflection at B and the slope at B. Deflection at B. Well, the deflection at B is the same as at deflection at x equal to L. B is at the end, right? B is over here. A is over here. And by the way, if you do deflection at A, you should get 0. So y at A, which is y at 0, becomes 0. That makes sense. So deflection at B, P over 6 EI, and I put in L for x, L cubed minus 3L cubed. So this is going to be negative 2L cubed P over 6 EI, and this reduces to negative L cubed P over 3 EI. So there's the deflection at B. Now, why is it negative? Negative means it's deflecting down. That's what I expect. I expect it to be a negative deflection. If it was deflecting up, it would have been a positive deflection. What else? The slope. The slope at B. I want the slope at B, which is dy dx at L, basically. Dy dx. I'm just going to use my equation for dy dx right there. That's, oh, well, I have it here too. Doesn't matter. 1 over EI times the quantity px. For x, I can put L. L squared over 2. And minus PL squared. C1 is 0. P for x equal to L. So that's L squared, that's L squared. So that's what I have. And so this will be a negative. P L squared over 2 EI. Okay. Now, why is the slope negative? Well, it should be negative. If I look at the slope of that point, if I draw a tangent, that's going to have a negative slope. that will have a negative slope. We're looking for slope at the end. So those are the answers. Any questions about this?
So will those equations apply to like all examples of deflection of beams, or just ones that are set up in this, which is like the one force on the end?
No, could be anything. So let's try another example. You can find, as long as you have the moment that describes the internal moment as a function of x, loading is irrelevant. The loading defines this internal moment. It doesn't matter, whatever loading you have, you can find the deflection. So let's try another example. This is problem 912. So in this problem, we have a triangular load distribution. So this answers your question directly. We don't have an end load, and we don't have a cantilever. We have simply supports. Last one was a cantilever. And this is made out of some material E, and some cross-sectional geometry defines I. And the magnitude of the distributed load at the peak is W naught, W0. And this has some length L. Here's my coordinate system. And what else? That's it. That's it. This end is A, this other end is B. I want to find the following. The elastic deflection curve. We want to find the deflection in the middle, L over 2. We want to find the slope at A at x equals 0. So those are the things we want to find. Okay, first thing we're going to do is find the reactions at A and B. And here's what we'll do. Let's see. Yeah, to draw a free body diagram. Have a reaction. Reaction B. S load is equivalent to a concentrated load of equivalent to the area of this triangle, which is half the base times the height, half the base times the height. And it is applied at 2/3 of the length at the centroid. Okay, so that is the equivalent load. So let's see, find RA and RB. I'm going to take a moment at A, and that must be 0. And then I'll have RB times L minus 1/2 W naught L times the distance of 2/3 of L. So 2 and 2 cancel. So end up with, I'm going to cancel one of the L's, divide everything by length. RB will be equal to W0L over 3. That's RB. And how do I find RA? And do I even need to find RA? I guess I just needed one of them. Doesn't really matter which one. Yeah, I'll find RA. I want to use the left side. So sum of the forces in the y equal to 0. That's what I should have done. taking a moment at B to begin with, but doesn't matter. In the y direction, I have RA plus RB. RB is minus. So RA is common denominator is 6. That's this one. Minus. Okay, that's what I have. So this becomes W naught L over 6. All right, so this is my RA. Okay. Any questions? So that's statics. So how do I find, so to use my equation, I need a function, I need a moment as a function of x. How do I find moment as a function of x? Well, I section it. I section on the original loading, not on this, right? The internal moment between this and this are completely different. The only thing that this is used for, replacing a distributed load with the equivalent concentrated load, is to find reaction forces. And that's the only thing. These two beams, if I load it with the concentrated load versus a distributed load, act completely different. Stresses are different, deflections are different. They're totally two different beams. But replacing a distributed load with a concentrated load will give you the correct reaction forces at the ends. Same reaction forces. That's why we do it this way. Okay. So I'm going to section it, and I'm going to derive the equation for internal moment. This is RA, which was U naught L over 6. This distance is x. The height of this, the height of that can be determined from similar triangles. Similar triangles say that the height of my original loading over the base of it, the length of it, is equal to, I'm going to call this h, h over x, h over x, similar triangles. H over x is similar to W naught over L. Therefore, H is W naught x over L. So that's H. It's the height of this distributed load. So here I have internal axial force and an internal moment. This is what I'm after. These are both drawn in a positive internal sign convention. I don't care about this. I need that. So I'm going to find that. So I'll do some of the moments at basically at X, at the cut. And I'll get what? I'll have mx. I'll have W naught L over 6 times x negative. And then I have a moment due to this. Well, the moment due to this is a concentrated equivalent times the distance from the centroid of it to where I'm taking a moment. The concentrated equivalent, well, this is the concentrated equivalent. Well, first of all, it produces a counterclockwise moment at x. X is this location. And that's a positive. So I'll take care of the sign. The concentrated equivalent, half the base times the height. That's the area of this triangle. You thought you were done with shear moment diagrams or finding equations for moments and stuff. You are not. This is gonna be with you throughout your careers in mechanical or any kind of engineering. All right, well, we're not done yet. This gives you the equivalent force. It will be applied at the centroid of it, which is 1/3 of x away from where I'm taking a moment. There. Any questions about that? So we're looking for mx. I'm gonna take that to the right. I'm take everything to the right side. W naught Lx over 6, and then I'll see if I can factor things out. And then this will be a negative. Well, it's an x cubed there, isn't it? W naught x cubed over 6L. So that's what I'll have. So there's my moment. I don't think I can do any. Well, I can factor out 1 over 6 and W naught, but I can do that later. I'm not going to do that at all. This is my equation. For the internal moment as a function of length, it's a function of x. So I'm going to go to my differential equation. Well, I'm going to multiply both sides by EI. That's this equation, right? Multiply both sides by EI. I get EI d squared y dx squared is equal to n of x. That's what I did. There it is. Let's look at boundary conditions. Let's look at boundary conditions. When I load this beam, what happens? Let's see. When I apply load, this triangular load, and this is supported like this, this thing is going to deflect. It's going to deflect more on this side, I think. I'm going to do this. Like that. But the key is what happens to the ends. There is no deflection. These supports will not allow deflections. So I can say that deflection at x equal to 0 is 0. Deflection at x equal to L is 0. Slopes are not 0. This will have a slope. This will have a slope. The only location or only condition where slope is 0 is cantilever. And on a cantilever, both the deflection and the slope is 0 at the support. On the simply support, it does not allow deflection. So the only thing you have is deflection. Slopes are not 0. Deflections are 0. So those are the two types of boundary conditions you may have. What time do I have? 10:30. Okay. Let's finish this and see what else we can look at.
So then what would be the angle at 0, at A?
That's part of the question.
Uh-huh.
What? That's something we got to find, right?
Okay. It's not going to be 0. We can't just determine that.
It's not 0, is it? Is it 0? I have a deflection here. I mean, I have a slope here. No, I don't have a deflection, but I have a slope. So if I draw a tangent line, that the angle remember the angle here is the slope.
So the deflection's 0, but the slope is not going to be 0. It's going to be negative.
Yes, the slope is not going to be 0. Slope at A is not 0. Slope at B is not 0. Slope anywhere is not 0. I mean, there's the curve. So when you think about slope, is the angle, if you draw a tangent at that point, is the angle that makes with the horizontal. It's called the slope. All right. In case of a cantilever, it will deflect like this. So if I draw a tangent, the slope is 0. If I draw a tangent here, I'll have a negative slope. So what I can say is here at A, I will have a positive slope. Here at B, negative slope. It should be a negative slope. At B, it should be a positive slope. All right, but I don't know. I have to calculate those. Matt, do you understand what I just did?
Yeah, thanks. I think I was confusing the cantilever and thinking about that one example. Yeah, that makes sense.
It's the slope of a tangent, right? You draw a tangent line at that point, it's the slope of that line.
Gotcha.
So if I draw a tangent to the deflection, this is the deflection, right?
Yep.
So this angle is the rate of change of y with dx, which is the slope. So it's the slope of this line, slope of the deflection line. This is the deflection. Okay, so just when you look at it, you can see that a tangent there is not horizontal. Therefore, it'll have, and it's going down, it's have a negative slope. Here, it'll have be moving, going up, so it's a positive slope. Okay, so there's my equation. I am going to integrate this. There's a square here. This becomes W naught L x squared over 12 minus W naught x to the 4th over 24L plus C1. I don't have a condition or boundary condition for the slope. I only have boundary condition for the deflections. These are my boundary conditions. There's 2 of them. So I cannot apply a boundary condition here. Take a derivative again. EI y of x is equal to W naught L x cubed over 36 minus W naught x to the 5th, 5 times 24. What was 5 times 24? 120? Yeah. Yeah. That's it. Plus C1x plus C2. Plus C1x plus C2. So now I can apply the boundary conditions. At y, deflection at x equal to 0 is 0. So this says that 0 is equal to, this is 0 minus 0 plus C2. So C2 is 0. The other boundary condition. Deflection at x equal to L is 0. Deflection at x equal to L is 0. So this says 0 is equal to W naught, I put L for x, L to the 4th over 36 minus W naught L to the 4th over 120. I canceled out one of the L's. Plus C1L, C2 is already 0. That's what I have. I can divide everything by L. So I get C1 is equal to W naught L cubed over 120 minus W naught L cubed over 36. I took these to the other side, and divide everything by L, so it'd be L cubes on both. And then common denominator, it's a 360, I think it's a common denominator. No, what is the common denominator?
360 works. I don't know if it's the smallest though.
I don't think so. I don't think 360 works. Does it? Does 360 work? Yeah, it does work. You are.
3 times 120.
Yeah, 360 works. 360 works. Let's do a common denominator, 360. So this will be 3, and this will be 10. So this will be a negative 7 over 360. So that's our C2. That's C2.
C1.
What?
Is it C1 or C2?
That is C1. C2 is 0.
Oh, okay.
That's C1. So did I do this right? 360. That's a 3. That's a 10. That's a minus 7. Okay, so that's C1. So I'm going to go back and input for C1 and C2. So I'll have rearrange it. Deflection. Elastic deflection curve will be equal to 1 over EI times the quantity W naught L x cubed over 36 minus W naught x to the 5th over 120 L plus C1x, and C1 is a negative, negative 7 W naught L cubed over 360 times x. Right, that's that equation. And then for C1, I put in 7 W naught L cubed over 36. I think that was, yeah, that's it. All right, so that is my elastic deflection curve. I can obviously factor out some things, and actually I can factor out what? I can factor out a whole bunch of stuff. But I'm just going to leave it at this. In my notes, it's reduced even further. I guess I'll just write down what I have in my notes. What did I do in my notes? Let's see. I factored out W naught over 360 EIL. Okay, that's what I did in my notes. If I do that, I get L squared. No, that's not. Yeah. I get 10. Anyway, this is, I'll get this. I'm just going to write it instead of wasting time trying to. That's this quantity. And then that's that one. Okay. That makes sense. All right, so that's what I'll get. That's an alternate form of that. So we're not done yet. That's my, now either answer is good, right? You don't have to reduce it down to exactly what I have in my notes or what I have in my calculation. This is sufficient. That is sufficient. But if you choose to reduce it even further, that's fine too. Either answer is acceptable. So we need the slope at A and we need the deflection in the middle. So let's find the deflection first. So I put in for X, I put an L over 2. And I guess I can work it a little further. 10 over 2 is 5. And then this is L to the 5th. And then this becomes minus 7. This is L to the 4th. Okay, this is 4. Okay, so this is 7 over 2. Seven L to the 5th over 2. There we go. So these are all L to the 5th power. So I can reduce these. Well, the common denominator will be what? 2? Minus 3L to the 5th plus 10L to the 5th minus 7L to the 5th power. Okay, so what is that? That's 0? Wait a minute, what have we done here? Oh, did I do that right? Oh, this is 2 to the 5th. I messed that up. It can't be 0. This is incorrect. 2 to the 5th, and this is 2 cubed, right? But this cannot be. I messed up a lot. 3 over 2 to the 5th power, and this is 10 over 2 cubed. Right there. 2 cubed, 2 to the 5th. So what's 2 to the 5th? (32) minus 3L 32 plus 10L to the 5th power 8 minus 7L over 2. Okay, there. That's much better. All right, but here's what I'll get once I reduce it. I get a negative 5 W naught L to the 4th over 768 EI. Right, don't ask me how, but this is after you reduce it, that's what you get. So that's a deflection right in the middle. So if I have a particular magnitude of the distributed load at its highest peak, if it's given to me, for this type of loading, or a particular length of the beam in a particular loading, and a given material and a given cross-sectional geometry, I'll just put in here and I'll find deflection. Is a deflection, this says the deflection at L over 2 is negative. Is that true? Well, yeah, it's below the axis. If it was above, it would have been a positive. The other thing we need is the slope at A. How much time do I have? I have 5 minutes. The slope at A should be negative. Let's see what we get. The slope at A, which is same as dy dx at x equal to 0. A is at x equal to 0. Dy dx. So I'll take that equation and I put in W naught over 360 EI L times, this will be minus 3x to the, no, minus 12 x to the 4th minus 30 L squared x squared minus 7L to the 4th for x equal to 0. That's 0. That's 0. At x equal to 0, right? So I end up with minus 7 L cubed W naught over, this is a W, not omega, right? 360 EI. This is the deflection at A, which is same as, I'm sorry, I said deflection, slope at A, which is same as dy dx at x equal to 0. So I have this negative, and that's what I expected. I expected a negative. Now, what is a deflection at B? I should have a positive value. Deflection at B is the same as dy dx at x equal to L. So let's see, at x equal to L. I'll use this equation, right? I know you can't see that equation, but I'm going to put in, for x, I'm going to put in L. Well, I'm going to take the derivative. I have an equation right there somewhere. There it is. Where is it? I have the equation actually right there. And C1. So I'll write the equation again for the deflection as a function of length. The slope is a function of length, sorry. Dy dx as a function of x. Right there. Write that equation. I don't have to put an x here. It's already implied. This is the equation for the slope. 1 over EI times the quantity C1, we have C1 right there. I write it somewhere else, it doesn't matter. W naught Lx squared over 12 minus W naught x to the 4th over 24L plus C1, and the C1 is minus 7 W0 L cubed over 360. That's C2, C1. C1 goes in there. So that's the equation for the slope. And I want to find the slope at L, which is same as theta B. Put in, for x, I put in L, so I get W naught L squared over 12 minus W naught, this is L cubed, L squared times L cubed. W naught L cubed over 24, one of the L's cancel, minus 7 W naught L cubed over 360. Common denominator is still 360, I think. Yes. Okay. So this is 1 over EI. Common denominator 360. 360 divided by 12 is 30. So this is 30. W naught L cubed. I should have factored that out. Minus 360 divided by 24. 15 W naught L cubed minus 7 W naught L cubed. So I expect a positive slope, and it will be positive. It will be positive, so I have this be 8 W naught L cubed over 360 EI. So this is the slope at B. And you can see it's a positive slope. Questions for me?
I don't have any.
Matt?
I'm all good. Thanks.
Okay. That's all I had. So on, we're on schedule for our notes we made earlier in the class. Where do I have 2 on 16 pages? 117. And this is 118. So next class we'll continue with beam deflection. I'll show you another method, and then I'll show you a third method using superposition. So there were 3 methods that I'm going to show you. And the third method using superposition uses existing equations for simple loading conditions that is charted in the back of the book in the appendices. So that would be an easy method if the loading situation can be matched to the loading given in a particular table. Okay, so that's all I had. Thank you very much. I'll see you guys next time. And meanwhile, email me if you have any questions.
All right, thank you.
Thank
See you
you.
Thursday.
Thanks. Have a good one.
You too. Thank you. Have a good Thanksgiving.